Okay, so I think we are good to start. Welcome everyone to the second Neutrino panel session of today, which will be mostly focused on low energy neutrinos and neutrinoless double beta decay. So for those of you who are tuning in today for the first time, it's probably good that I explain first how these panel sessions work. So the idea is that now we have our 6 speakers from the asynchronous talks connected. You can see displayed there a list of speakers. And while you cannot ask them question directly, what you can do is write your questions in the Q&A panel that you find on the lower right in your Zoom window. And then I will ask the questions for you, and hopefully our speakers will answer them to your satisfaction. For sure they will. Okay, so what we should do first is that we do a short round of introduction of the 6 contendants. The one thing that we should do first, though, is that I remind you that those of you who have just been at the poster session, that there is a poster voting that you still can participate in, and which will get the results later on. Okay, so going to our 6 speakers. So I would ask you all to introduce yourself for half a minute or so, just following the order like you are displayed now on the slide. So Alessandra, please take it away.
Okay, hi, I'm Alessandra Re, and I'm a researcher at the Milano University in Italy, and I work mainly in the Borexino and Juno collaboration.
Okay, thank you. Christoph?
Hello, my name is Christoph Wiesinger, and I was talking about the search for neutrinoless double beta decay in germanium-76. So namely about the final result of the GADA experiment and the prospects of Legend to go beyond that.
Okay, thank you. Madhurima?
Hello, I am Madhurima Chakravarti. So I am a researcher in IIT Guwahati, India. So I have talked about fast flavor supernova neutrino conversions in 3 flavors.
Okay, thank you very much. Roger?
Hi, my name is Roger Huang. I'm a graduate student at UC Berkeley. I work mostly on the Cori and qubit experiments, and I presented the most recent results from Cori.
Thanks. So we switch over to Rudolf.
Yes. Hi everyone. So I'm Rudolf Rogli, a PhD student at Saclay in France, and I worked on the stereo experiment and the latest results reported by this experiment on the measurement of the purified international spectrum.
Thanks for that. And then lastly, Stefan.
Hi, so my name is Stefan, and I will talk about how unstable neutrinos can relax the cosmological mass bound on the neutrinos. And yeah, I'm also a PhD student, but in Valencia, Spain.
Okay, thanks a lot. This is our panel. Now, so while I ask the participants to type in their questions, maybe I can start out asking a first question to Alessandra's talk on Borexino. So one thing I was wondering, listening to the talk again, is how much the new result on CNO neutrinos is depending on knowing the spectral shapes of bismuth-210 and carbon-11 and CNO, of course. Can you comment on that?
Yeah, sure. I don't think I need a slide maybe, but I don't know. Anyway, it's obviously a key part of the analysis, because otherwise, without a spectrum, you cannot build a PDF, and without a PDF, you cannot help your fit to disentangle within the contribution. So actually, there was a parallel work. I did not discuss it in the talk, but there was a parallel work to study, and the best up to date and up to now bismuth spectrum, of course, because it's fundamental. It was done actually in Germany, and then the latest measurement was done in Dresden by the group of Kai Zuber. And anyway, we include, of course, there is a we assume a spectrum of bismuth, and it is there. Anyway, the systematics between different spectra were taken into account, of course, because we decided for the best, but we included a systematic into our counting for the error. And the same actually for all the other species for the spectrum, because it's how the fit works.
And do you have kind of an order of magnitude of how much does it impact on the overall systematic error?
Well, I don't think I have it there in the slides, but I can retrieve it. Just give me 1 second. Here. Just to give you the number correct. I don't want to mess it up. Okay, the systematics are there. Okay. Well, it's for the bismuth, which is the most problematic, let's say. We have different references for the beta spectrum with a difference around 18%. So it's one of the really main contribution of the systematics error in the CNO analysis.
Okay, thanks a lot.
You're welcome.
Okay, so let me go on, and it's again a question about sensitivity, but this time to our Gerda speaker. So in your talk, you showed two kinds of limits, one Bayesian, one frequentist. And I noticed that I think the frequentist one is the stronger one. And I was wondering if you can say a few words about where the difference is coming from.
So yes, maybe we can go to that slide. So we have the numbers there. I think it was slide number.
Fortunately, I did not write it down, sorry.
No problem, I have them here. So it's slide number 9. So if you go ahead. Yes, I was putting that numbers there. So we perform both the frequentist and the Bayesian analysis. I mean, in the frequentist case, we got this 1.8 times 10 to the 26 year of lower limit, which is actually, I mean, coincides exactly with the median sensitivity. So we hit directly that. We do also the Bayesian analysis, but there, of course, our limit depends on the choice of prior very much. So if we perform this with a flat prior on the rate itself, then we obtain this 1.4 times 10 to the 26, which is a bit weaker, but also coincides numerically with the sensitivity for that case. But if we assume a flat prior on M beta beta, and as you know, there's like a square root dependence, then we get even a stronger limit. So we quote all of that numbers, and then of course, I mean, it's the choice of the reader which statistical framework you want to take. But I mean, in the end, our main result is the frequentist limit.
Okay, so in a way, the Bayesian one is a conservative version, right? So yeah. I was a bit surprised because usually they are a bit better. So, okay.
Yeah, also in that case, unless we choose a different prior.
Okay. Okay, thanks a lot. Then I would like to ask one question to Maturima about the supernova neutrinos. And that is something that I was wondering while listening to this, listening to your talk, is about this possibility to create muons in a supernova in the neutron star that is emerging from a supernova explosion. So I was under the impression that the temperatures are not high enough in order to create a muon, but maybe you can tell a bit more about why muons play a role in neutrino emission.
Okay, so usually it is thought that usually it is taken that there are no muons in the supernova, but recently there was a paper which showed that in the accretion phase, like I showed that there are 3 phases of neutrino emission. So in the accretion phase, the temperatures are so high that there is a possibility of creation of muons. Through the pair production, muons can be created. So due to which usually the neutrinos are created only means the electron neutrinos are created from the charge current interactions of electrons. And since there are no muons, so the muon types of neutrinos are not created from the charge current reactions. They are only created through the pair production processes. But if there is a possibility of muons, then the new mu's can also be produced through the charge current interactions of muons. So that is the case. Like, means in the accretion phase, the temperature is so high that it is possible to create the muons.
Okay, I see. And you already explained my follow-up question, how it does influence the muon neutrino production. Does it have some influence on the tau flavor as well?
Yeah, but I mean, the impact on tau is not so much. Like, there is a greater asymmetry. Like I talked about the asymmetry. The main thing is that there is a asymmetry between nu mu and nu mu bar, which is not there if there are no muons, which is assumed to be almost equal if there are no muons. But on the tau, it is the effect is not much.
Okay.
Means temperatures are not so high that they can create tau also, but the probability of that is less as compared to muons.
Okay, thanks. That was really enlightening.
Thank you.
Okay, let me go on asking Roger about something I was wondering for Core. So I saw in the data quality cuts that there are several crystals that have still are quite good, but considerably worse energy resolutions than the other crystals, so 19 keV or larger. Can you comment a bit what makes the difference between different tellurium oxide crystals, how well the energy resolution ends up to be?
Yeah, so there's a number of things that affect this. One thing is just the quality of the crystal itself. There's some natural variation, and depending on how nice the shape is or the general quality, it can affect how phonons behave inside it, which affects the resolution we can end up getting. The more significant factor probably is just the NTDs, the DD germanium thymistors that we use on each of them themselves. There's some variation in the quality of these as well. And in general, we saw during core commissioning that a lot of the NTDs had a much larger resistance than we originally expected for the temperature we were operating at. So some of them may be in a somewhat suboptimal regime, and this is likely a contributing factor. And then besides that, there's the side of the electronics, the front-end electronics themselves that we use to read out each of the crystals. From the combination of all of these, this gives us sort of different noise conditions across a number of the crystals, and in particular across some of the towers that we have. And this gives us this kind of tail to the distribution. The hope is that we can kind of rein in this tail for Cupid with better controls on the crystals and the NTDs themselves when we actually commission it.
Okay. Thinking back of dark matter experiments, is there also an influence of how well your NTD is coupled to the crystal? So does this have an influence on your resolution as well? Or is that?
It could. It could, but this isn't something that we've been able to test with the core crystal specifically, since we've never fully opened up the cryostat since closing it. But we expect this is something that we can look at once the cryostats open after core is done. And the information from this can hopefully inform what we do for Cupid.
Okay, sounds fair. And then I have a connected question that actually goes again at Christoph. So in GERDA, of course, you have many different kinds of crystals or detector shapes, I should say. But within one detector shape, do you see a similar variation in performance of the detectors? Or is it more uniform?
We see some variation. Oh, sorry. That was no problem. So we see definitely some differences in resolution, which are, I mean, the detectors have different performance, but this mainly depends on the shape. And since we have these three different detector shapes, we have mainly three different classes that behave a bit differently. But in general, the fluctuations are not that large. I mean, in the beginning, we were always doing an analysis where we had actually only one resolution per detector class, but now we went to in our analysis that we take into account each detector's resolution individually just to perform a bit better, but the variations are not that large.
Okay, I see. Roger, would you want to chime in on that again?
Sorry, say again?
Okay, I wasn't sure whether you had an additional comment to that, but if not, it's also fine. Sorry.
No.
Okay, very good. So let me move on, asking a question to Stefan this time. And that is a question about whether solar neutrinos and supernova neutrinos can provide useful constraints on the neutrino mass bounds, or whether this baselines are simply too small for that. So the question is about whether the decay
Okay,
of neutrinos.
yeah, I see. Yep. So yeah, actually there are constraints from supernovas, but for the most promising case of the two-body decay, which I was talking in my presentation, right? So the best constraints come actually from the CMB and large-scale structure. But if you analyze, for example, three-body decay, where the mass of the phi or the Z prime is can be heavy, right? Because it's a mediator. So you would have like a decay of a neutrino into 3 stereo neutrinos mediated by a phi scalar boson, for example. Okay, and the scalar boson can be from EV range to MEV range. And there, in fact, we have supernova bounds, and actually they are quite strong for high masses of the scalar boson, which then excludes the possibility of the three-body decay. So yeah, we take them into account, and that's why three-body decays are basically excluded. Okay, but in a two-body decay, which I was talking in my presentation, they are not relevant. Okay, simply because of the mass of the boson has to be lighter than a light neutrino, right? Because the neutrino has to decay. So they are like sub-EV, and there are no supernova constraints.
Okay.
I hope this answers the question, no? I guess.
I think it answers the question. I'm not sure I have fully wrapped my head around it, but yeah.
So, sorry?
I'm just wondering myself whether I understand, I fully grasp why it's so different. Okay, but I can accept that it's simply not powerful enough. I mean, for the constraints from 87A.
Yeah, I mean, the difference is if you analyze these two decay channels, right? It's a two-body decay. So if you have a final state, the boson has to be sub-EV, right? And the supernova bounds get strong for higher masses of the boson, okay? And so it's more applicable for three-body decays, where the boson is a mediator, so can be off-shell in this decay.
Ah, okay.
Okay.
Yeah, now I got it. Thanks.
Oh, thank you.
Okay. I have another question, but this time for Rudolf on stereo. Something I was wondering is that, I mean, a lot of the problems or the difficulties of doing this reactor experiments very close to the reactor core is that you have this background, intense background from the core. And so in your talk, you described about taking reactor off data. So what else is needed in order to get a good impression about what is the actual background level if the reactor is on? So how is this constrained? Rudolf, you're muted. Sorry.
Yes, my bad. Sorry. So your question is about basically the extraction of the neutrino signal from the overall signal.
Yeah, about the reactor on background. So how is this estimated?
Yeah. So actually, the disparation actually between the let's say background events and the neutrino signal IBD events is actually made possible through this pulse shape discrimination that we're doing in stereo. So that enables to actually separates, let's say, so the electron-like recalls, so in which the neutrino the neutrino IBD events occurs, and the proton-like recall. And so this is what actually enables us to achieve this signal of a background roughly of signal overlap ratio, sorry, roughly of 1 on the overall signal of the overall signal energy range. Sorry. So actually, the analysis for the signal extraction is actually done through several steps. So first of all, there is those section cuts, so section cuts on energy and on the topology on the events, and then we apply this post-shape discrimination for particle identification that enables to extract this neutrino signal in rectangular period with respect to the assessed background.
Okay, and then a follow-up question. That is a follow-up in the sense that it's also in stereo. So you're showing this analysis of the 5 MeV bump for stereo alone, and then also in combination with prospect.
Prospect, yeah.
Yeah. So, and you have also shown beginning of a combined or preliminary results from a combined analysis. And my question would actually be, so it seemed in the plot that the 5 MeV bumps in stereo and in prospect are not exactly at the same position. Can you say something about that? Or would you say that it's just statistics, bad luck or luck?
Yeah. So actually, those, as I said in my presentation, so those results are really preliminary, and so they will be, let's say, the subject of the dedicated publication. So what I will state today is very preliminary, but what we observe is that the distortion that we see, stereo experiments and the prospect experiments, so in this 5 MeV region is not actually, let's say, are not actually the same. So we're not strictly speaking observe the same distortion, but when we perform this chi-square test, that is in my presentation, so on the overall unfolding range, we see that that both of our data sets, so stereo and prospect, seem to be statistically compatible, so on the overall energy range. But that's right, that's for now. So if we focus only on this 5 MeV region, apparently we do not, strictly speaking, seem to see the same distortion. But still, what the chi-square comparison tells us on the overall energy range is that both data sets seem to be statistically compatible, and so this, even though by eye, let's say, so naively we would say that we do not see the same thing, it seems to be still statistically consistent. So actually with this joint analysis, given that we are not basically reconstructing the same distortion, so it is because what we would want to quote, let's say naively, is by combining those two experiments we might increase the sensitivity to this 5 MeV bump. But this is not so simple, because this is only in the case where both of our data sets are strictly speaking, let's say, not only statistically compatible, but comes from, let's say, the exact same spectrum, which is what is expected theoretically. But given that there is this extraction that we do, so to extract our signal, so there may be some statistical effects that are not really accounted for before those two analyses. So what I mean, sorry, is that so by merging those two experiments, so one, our goal is to, let's say, is to produce, let's say, so this one and unique statement on this 5 MeV bump for the U5 anti-neutrino spectrum. But for instance, this, let's say, we could not, let's say, naively expect, for instance, to increase the sensitivity that we would quantify for this event excess with respect to the one, for instance, that was reported by the stereo experiment only analysis, and that was reported in a previous publication. So, for instance, the stereo reported an excess of 3.5 sigma. So in this 5 MeV region, so just just by the analysis of its unfolded spectra. But this is for the stereo only bump. But given that for this joint unfolding, so we're basically merging so the stereo bump with the prospect bump, which is not speaking the same. So we should not expect, let's say, naively a 4 sigma or 5 sigma significance, because basically we are just averaging, let's say, those two bumps in the common unfolded spectrum that is to be produced. So just to be perfectly accurate on this shape analysis.
And last question to this. So if you compare this now to these measurements done by Daya Bay a couple of years back, where they try to align these differences in event rates in the anomaly to uranium-235. So are there some plans for a combined analysis with that in order to come to the source of this 5 MeV bump?
So this is something that we are truly considering and that we are thinking about. So first of all, so we want to finish this joint study with the prospect experiment, so to see what we can state, and then that's right, that let's say a natural extension would be to consider so the results of experiment that such as Daya Bay, to have a final statement on this 5 MeV bump and on its, let's say, relationship with the fuel composition. So this is, let's say, something that we are seriously considering, but right now there's nothing really, let's say, concrete.
Okay, thanks a lot. Then let's switch gears a bit and have a question to Maturima again about supernova neutrinos. And the question is about the spectral swapping in a 3 neutrino flavor model. So are there effects, measurable effects, that would appear if you consider a 3 flavor model instead of only 2 flavor models that you also showed?
Yes, so yes, spectral swaps are still visible in the 3 flavor models also, but here and that is in the case of slow oscillations, but here what we have done is we are focused on fast oscillation. So I mean, I cannot tell you exactly what are the differences, but yes, in 3 flavors also spectral swaps will be seen.
Okay. And more generally speaking, so would this still be that experiment should look for, the spectral swaps in different neutrino channels?
Sorry, can you repeat the question?
So my question again is, so is for the effects that you have been describing, is the best experimental signature still to look for the spectral swaps in one or several of these neutrino flavors?
Means these spectral swaps are actually the effect of collective. These are a result of collective oscillations, but means generally there is a very there is a very less probability of seeing this signature, but yes, normally the experimental signatures are basically of the MSW effect is seen. So collective oscillation possibility is less, but yes, there should be some. Means I don't know exactly what is the experimental signature, but
yeah, in the end, you get a deformation of the energy spectrum that is gives you something. Yeah. Okay. Okay. Thanks. Then to stick a bit with theories, there's a question about to Stefan about this light scalar decay products that you get in your 2-body decay. So are they also thermally produced, and would they contribute to an effectiveness in the early universe during Big Bang nucleosynthesis? And is this already considered in the calculations that you have done?
Yeah, I see. Very nice question. In fact, yeah. So this is already considered, and it's a weaker bound than the bounds the bounds I showed in the presentation. So the ineffective constraint from BBN is something like that. N effective has to be less than 3.4. Okay, so then running the analysis of BBN, which so taking into account the light scalar boson, we get the constraint on the coupling, which is like 10 to the minus 6, 10 to the minus 7, something like this. Okay, which is weaker, the bound is weaker than the one from Planck. So in fact, yeah, there's a constraint from BBN and we take it into account, but it's not relevant in the parameter space we consider.
Okay. Okay. Very nice. Okay, yes. Now, I think we are actually already running out of time. So since I see no further questions posted, I think we should probably conclude. So thanks to all of the speakers and all the panel and also for our participants to hand in so nice questions. And yeah, let's move on